Hello and welcome to my little video on the principles of resistance and power transfer. When working with electrical circuits and designing them, it seems kind of obvious, but maybe worth stating, that we want to transfer as much power from our voltage source to whatever our load is. And the makeup or the resistance of our load will have a definite impact on that. That seems pretty obvious, pretty intuitive. What's counterintuitive is the relationship between the load and the source and how we get maximum power transfer. In this case, I've drawn a simple circuit we've seen a lot in basic DC as you're learning basic DC theory with a source and two resistors. This resistor is the internal resistor. All sources have an internal resistor, whether it's a battery that has some internal resistance to current flow, a generator, it doesn't matter. They all have an internal. In this case, we're just saying that it's the internal resistance of the battery, but the principle applies anywhere. And what we're trying to do is transfer the power, the electrical power, to the load. And it doesn't matter whether the load is a motor, like a hydraulic motor, or a light, or a hot air popcorn popper. Doesn't matter. These principles all apply. It does make sense that the size of this resistor would affect power transfer. That's pretty intuitive. The way it affects it is not so intuitive. So let's take a look at some numbers. Let's take this same circuit and we'll say that our internal resistor is 10 ohms and our load is 20 ohms. Now, first off, of course, no power source is going to have an internal resistance of 10 ohms. It just makes the math work better. So in this case, our total resistance in this circuit is 30 ohms. And we know from Ohm's law that the current is equal to the voltage over the resistance, in this case 12 divided by the 30. So we get a current of 0.4 amps. Basic Ohm's law DC circuits, the voltage dropped across the load now is 0.4 times that 20 ohms. We get 8 volts dropped across this resistor. That makes sense if we think about it. This resistor is 2/3 or twice as big as this one, so 8 volts here, 4 volts there. That's making sense. Power, we know, equals current times voltage, so power is going to equal 0.4 times my 8 volts, 3.2 watts. So there we go. In this case, we get 3.2 watts. Now let's look what happens when I decrease the size of the resistor. What do you think is going to happen? Will power increase or will power decrease? Who knows, right? Well, let's start out the same way we did before. RT in this case equals 15 ohms. 12 divided by 15. The 12 divided by the 15 equals 0.8 amps. So we see that our current increased. That makes sense because my total resistance decreased. The voltage dropped now across this 0.8 times 5 is, I've only got 4 volts dropped across that resistor. All that makes sense. Let's look what happens to power now. 4 times 0.8 equals 3.2 watts. Power neither increased or decreased, it stayed the same. I decreased the resistor and power still didn't go up. That seems odd. Let's look at the third case. Here I have 10 and 10. So my total resistance, of course, is 20. Let's take 12 divided by 20. We get a current of 0.6 amps. Makes sense, halfway between the two. The voltage dropped across there. You ought to be able to figure this out pretty quickly, but let's say 0.6 times 10 is, of course, our 6 volts. That makes sense with a 10 ohm resistor and a 10 ohm half of it. Let's look at the power. Power 6 times 0.6 is 3.6. So when my load resistor matches my internal resistor, my power increased. That seems pretty crazy, doesn't it? Let's take a look at some extreme cases. Let's assume that the load resistor is 1 ohm. In this case, we have a total resistance of 11 ohms, right? So my current is 1.09 amps. Current went up. The voltage drop then is, of course, because we said this is 1 ohm, is 1.09 volts. So let's take 1.09 volts times 1.09 amps, and we get a power of 1.18 watts. So we've decreased our load resistor extremely, and my power has gone down quite a bit. That's the counterintuitive part. I decrease the load from 10 ohms to 1 ohm, and my power drops by a factor of 3. Let's go the other way. Let's make our load resistor 100 ohms. In this case, my total resistance is, of course, 110. So here, my total current has decreased by a lot. It's 0.109. And then that means the voltage dropped across there times 100 is E. Our load will be, we're going to have 10.9 volts. So let's look at our power. 10.9 times 0.109. And again, we get 1.18 watts. Again, now I've greatly increased this, and you can see my power has still decreased. To show this graphically, here when I had my load resistor of 1, I had a power of 1.18, 5, 3.2, 10, 3.6, 20. So let's make a little graph. This graph isn't perfect and linear because I go from 1 to 100, but this is RL and this is power on this side. So when I had 1, I had a power of about 1.18. Let's put that there. 5 was about 3.2. 10 went up to 3.6. 20 went back down to 3.2. And 100 went back down to 1.18. What we've done here mathematically is we've just demonstrated that maximum power transfer occurs when the load impedance is matched to the source. And this is why terms like impedance matching are such a concern in circuit design. Thank you for watching this video. I hope you found it helpful.